instruction, which was probably a little bit faster than I do it here, that you also think you deserve a break. I don't know. But so I'm at least happy that you are here. Today we will continue a little bit on the Diels-Alder reaction, and depending how fast I will be, we will also move a little bit to 1,3 dipolar cycloadditions. In the handouts you have on the Diels-Alder reaction, you have many more examples than I will cover here. So please, again, have a look at them. See if you can rationalize, if you see starting material and product, if you can rationalize the reaction. Of course, there's no need to memorize these reactions, but nevertheless, make sure you can understand them. However, I would like to point out a few notable examples of Diels-Alder reactions. So far, the one structural element obviously you should associate with a Diels-Alder reaction is the cyclohexane ring. So whenever you think or you see a molecule which has a 6-membered ring, you can think of this as the minimal structural element for a Diels-Alder type reaction, and then you can think if you can make that molecule, for example, by a Diels-Alder reaction by somehow appropriately disconnecting the 6-membered ring. And of course, keep always in mind that by simple hydrogenation, you can convert a cyclohexene into a cyclohexane. So in principle, by this transformation, again, also each saturated 6-membered ring you see, in principle, you think is Diels-Alder reaction a strategy to make that molecule. And of course, you know that this Diels-Alder reaction I have written here is not working very well unless you have substituents here, donors raising the HOMO and the LUMO, acceptors lowering HOMO and LUMO. So this is a good combination. Typically, to make a pattern like this. This is the so-called normal Diels-Alder reaction or normal electron demand. But the inverse is true as well. It's just not as common that if you have an acceptor substituted diene and a donor substituted dienophile, by the same way Diels-Alder reactions will proceed well, and that is a so-called inverse electron demand Diels-Alder reaction. So far so good. There have been some very successful dienes, and I think I had it already last time on the slide, with electron donating dienes, and one of them is this diene, which you get from the corresponding beta dicarbonyl compound by enolization. And this is the so-called Daniszewski diene, after the inventor, Professor Daniszewski. Electron-rich diene, extremely reactive, very often already at low temperature, minus 40, minus 78 degrees, and it will readily react with acceptor substituted dienophiles. However, the structural element you have to think here is not just a cyclohexene, as you will see just in a second. If you use this type of diene, you actually create a cyclohexanone. And the reason for this is that after the initial Diels-Alder reaction takes place, put it in this way, once you hydrolyze this silyl enol ether, you will create a cyclohexanone here, and under the acidic conditions, protonation and elimination of methanol will occur. Which then will give you this cyclohexanone. And again, not only that this works very well because it's a very electron-rich diene, but obviously you make a very useful structural element here. Because as you know, alpha-beta unsaturated carbonyl compounds, of course, can easily functionalize in further reactions. Now, since carbonyl compounds are useful for further functionalization, there are a number of other interesting dienophiles. And one of this I would like to introduce to you. This is alpha-chloro acrylonitrile. And this is the equivalent, if you want to do a Diels-Alder reaction, with a ketene. Ketene is not easily to synthesize. It's a gas. It's not commercially readily available. This compound here is, if you let this undergo the Diels-Alder reaction, what you will observe is the normal Diels-Alder product you would expect, usually with, again, the pi substituent in the endo position. And we talked about that still not completely understood rule that pi substituents usually prefer the endo position for the secondary overlap of with the developing pi system. Now, if you treat this compound with KOH, what is going to happen is that you will do a substitution on that chlorine atom Let's not specify the stereochemistry here. And then, since cyanohydrines are not very stable, and cyanide is a very decent leaving group, you will actually extrude under these conditions cyanide or HCN, and you're creating a carbonyl compound here. So if you look at this, this is as if you would have done the Diels-Alder reaction of cyclopentadiene with ketene. And again, having a carbonyl functionality here is very often useful, so that has been a quite often applied dienophile. Do we lose lights? Now, another important thing to keep in mind that also heteroaromatic compounds which are readily available are good dienes in the Diels-Alder reaction. Cyclopentadiene, of course not a heteroaromatic compound, is one of the most reactive dienes because it has already the preferred conformation to undergo the Diels-Alder reaction. However, there are a number of heteroaromatic compounds out here which you can view as analogs of cyclopentadiene. So furans, thiophenes, and pyrrole have the same structural feature. However, in general, they are less reactive because if you do a Diels-Alder reaction, you have to break the aromaticity of that system. But nevertheless, with appropriate dienophiles, this is possible. And let me give you a famous example. If you treat this substituted pyrrole derivative with this acetylene, and again keep always in mind that most of the Diels-Alder reactions we have written up so far, the dienophiles have been an alkene. However, alkynes are reacting as well, and in many cases they are even more reactive than the corresponding alkenes. And especially such sulfonyl substituted alkynes are highly reactive dienophiles. And that is, for this particular reaction, important because pyrrole, being from these three heteroaromatic systems the one which has the highest aromaticity, is the least reactive diene in a Diels-Alder reaction. And to give you an idea, this reaction works well at a temperature of 85 degrees. The one thing you fight in these type of Diels-Alder reaction always, and especially when you have an aromatic diene, is that these type of reactions are also reversible. And so especially if you would now say, oh, this is 85 degrees, 24 hours, I want it faster, and you heat it up more, very often under the high temperature conditions, the Hetero-Diels-Alder reaction becomes the major process, and all you will see then is that you will reisolate starting materials. So it's a trade-off. Very often you need a very reactive dienophile. You need to find the right temperature conditions or Lewis acid catalyzed conditions. We will go into Lewis acid catalysis in just a moment. But then nevertheless, these type of reactions work. And this compound has made in the beginning, middle of 90s, was a sought after intermediate because subsequently this Diels-Alder product can be converted into this molecule, and you can probably see how this is being done. You have to hydrogenate the double bonds here. You have to take off this ester group, and you also have to take off the sulfonyl group, which the latter can be achieved by reductive chemistry. I don't want to go into this specific reaction. This compound is called epibartidine. It is isolated from the back of a South American frog. It was noticed that a lot of the natives liked these frogs, and they would catch them, and then they would lick their backs, because what happened is that you became immune against pain. And it turned out that this compound is about 200 times more active than morphine. And on the same time, you know what the big drawback of morphine is. Morphine makes you dependent. So if you had like a severe accident as a young person where you are in great pain, nevertheless, doctors will be reluctant to give you morphine because they are afraid that you might develop a dependency. And this molecule was not interacting with the receptors which are responsible for making you dependent on that, but nevertheless were very, very pain effective. And so you can imagine also a very simple molecule. Many programs in industry started to develop this into a drug. Today, 15 years later, and probably more than 500 analogs of these compounds, we still do not have a drug. The problem is that this is an extremely good painkiller. However, it's toxic, and the toxicity in the moment cannot be handled, and especially the toxicity is from human to human apparently very different, and so it might save or it might kill the pain of one person, but the same dose might actually kill the next person. And so that is something which in the moment still has not been solved. Okay, let's look at a Another strategy. Let's look at Lewis acid catalysis. And so the typical scenario, if you want to catalyze the Diels-Alder reaction, is that you have your HOMO of your diene the LUMO of the dienophile, and by the interaction of these two orbitals, you will undergo the Diels-Alder reaction. And what the let me also put the HOMO of the dienophile also somewhere here. And by coordinating a Lewis acid to the dienophile, let's take acrolein as the example here. By coordinating a Lewis acid, what will happen that by roughly, there have been calculations on this, but by roughly 10 cal per mole, you will lower both HOMO and LUMO in the Lewis acid complex. And so obviously, this interaction now becomes much better. The closer HOMO and LUMO are together, the faster the reaction is, and therefore you can greatly accelerate these type of Diels-Alder reactions by Lewis acid catalysis. However, you will not only accelerate reactions, but it will also have a very interesting and pronounced effect on selectivity. And let me show you an example for this. So let's analyze this Diels-Alder reaction here. And again, it doesn't make sense really to memorize which product will form or which product will now form preferentially, and you will see that selectivity is now changed with Lewis acids, which we will add. But here's what I think you should be able to analyze here. So obviously, this is the diene. This is our dienophile. In our dienophile, however, we have two double bonds which could react. Now, if this is an electron-rich diene here, and this should be the electron-poor dienophile, as you can see by these electron-withdrawing groups here, and you know that the more electron-poor your dienophile is, the better the reaction should be. In this analysis, this should immediately tell you that this should be the double bond which is more reactive, because this one has a much stronger donor attached to it than this one here. The next thing you should be able is, if we draw the product, and let me draw now a product where we connect the atoms in this way. But you should realize, since this is an unsymmetrical diene, that this is the one regioisomer which could form. And let me draw this. But that at the same time, this diene could have flipped by 180 degrees, having this metal group on top, so that the other regioisomer should be this one here. Now, in this course of this reaction, we are creating, in this particular one, we are creating 3 new stereocenters. You should again immediately realize that in the absence of any chiral information, which we have here, that you will form these regioisomers as a racemate. However, the relative configuration here is not necessarily all random here. The one thing we should see is that since the Diels-Alder reaction is stereospecific, meaning that if your substituents in the diene and in the dienophile, the type of geometry they are in your starting material will be the same, will have the same relative configuration in the product. So since these 2 substituents are cis here, they should also be cis in the product. So this certainly is determined here. However, now the relative stereochemistry between these 2 centers will be determined by the transition state the reaction can pass through. And if you draw your diene like this, there are 2 ways your dienophile can approach your diene. And this is that, so these centers are reacting. And once the substituents, the pi system on the dienophile can orient itself into the pi system here, this is again the so-called secondary orbital interactions. So this would be the so-called endo-transition state. Or the alternative would be let me see if I get this. That you flip your dienophile around, and so that this is pointing away from your diene. So this would be the exotransition state. And now assuming that we have, in this case, endo control, as we take as a general rule that endo products should be preferred in, in these type of reactions, then you need to come to the conclusion. And again, I would like to ask you to either draw a model or draw it on paper out, but you see that this methyl group is pointing away, and this methyl group is also pointing away. And this leads that in this endo product, both of these methyl groups should be anti to each other. And so this would be the relative stereochemistry under the presumption that the endo products will be formed. This is what you would predict. Now let's see what happens here. Do we have, in terms of this regioselectivity, do we have any type of preference? If you look at your diene here, this is more or less, although unsymmetrically, but it's electronically not very differentiated. If anything, you would say that this is a donor here, and so by this type of notion, if you have a donor here, if you would have some polarization, which nevertheless would be not very pronounced, if you would have any polarization by this donor, you would say that this end might have a very small negative formal charge here. However, if you do this reaction, and if you just heat the two products 100 degrees, no Lewis acid, you will form both of the products in a 1-to-1 ratio. Again, clearly because this double bond is not very differentiated. Look at this, same thing. It has a methyl group here, it has a donor here, but as we all know, it's a weak donor, and these type of carbonyl groups probably will not be able to, or are the same, so the differentiation is clearly very minimal here. However, now the interesting thing occurs if you take Lewis acids like boron trifluoride as in diethyl ether, so you have a boron trifluoride etherate complex, you will form these products in a ratio suddenly of 4-to-1, favoring the left diastereomer here. And if you take tin tetrachloride, let me just if you have tin tetrachloride with high preference, you will form the other regioisomer. So that's the first thing which is interesting. Although, as we said, the electronic differentiation here in diene and dienophile of the double bonds is not very, very strong. Apparently, Lewis acids are able to make that differentiation more pronounced, and especially as you can see here, the Lewis acid somehow has to interact with our dienophile, and therefore something must be happening here. Does anyone see why in what these two Lewis acids are different. Why is there a conceptual difference here? Yeah. The one is hard and the other one is soft. And I'm almost afraid to ask you which one you would think is hard. Which one would you assume is hard? Yeah, I would also, if I would go on this line, the argument, the boron trifluoride is the harder one than the tin tetrachloride. Main group, early period metal, very strong electron withdrawing substituents. Probably that it would be the harder one, although I can tell you that there's also main group metal. It's both very hard Lewis acid. Now this type of argument would help us if the carbonyl groups would be also differ in softness and hardness, which would not be here really obvious, right? It's both times the carbonyl group in an alpha-beta unsaturated system. I could walk the line here and say they differ in hardness. I think I would have a very tough time here arguing that any of these two carbonyls should be different in hardness. Because you will see in a moment that this is what it will be about, that the Lewis acids will coordinate preferentially once on this carbonyl and once it will on that carbonyl. Any other ideas? What would be different of these two Lewis acids?
The other one's conjugated with substituent.
Wait a minute. The other one, which one? The carbonyl groups. Okay, so the carbonyl group is
The other one's
conjugated with what? With a double bond? To the methoxide. Okay. So what is realized here, and so your argument is an interesting one, because what you are proposing now is that, hey, wait a minute. Maybe these two carbonyl groups are different. Who's closing the lights here all the time? Well, that's very interesting, because I just said they are not different, right? But here you come with a very interesting argument and say, shouldn't this carbonyl group here be more electron rich than this one? Because here I cannot do an analogous one. So, interesting. So we would say that this is, let me not put a delta minus here. We would say this is probably more electron rich because it benefits from the donation of this, while this carbonyl would not. If anything, then the inductive effect here would make that less electron rich. Okay, so we have a difference then indeed. So you would predict that a Lewis acid, if it has the choice, would prefer coordination with this one rather than with this one. And that is already one of the arguments, and we will see that boron trifluoride, if I say this is carbonyl group A, that boron trifluoride indeed, or I can just put it on here, of course. Boron trifluoride indeed will coordinate with this carbonyl group. And so what is happening this way? This way, electron density is withdrawn from the alpha-beta unsaturated system, but of course, again, by a resonance argument, it is specifically withdrawn from this carbon here. And now if this carbon is more the delta plus carbon and this carbon is more the delta minus carbon, sorry? Here? Why do you want the delta minus here? Because I'm now also because I have drawn the selectivities the wrong way here. So it's 1 to 4 and 20 to 1. Now, by the argument of resonance, if you withdraw electron density here, you make this carbon more positive, and then you make the conjugated one more positive, right? Because again, I can, if I draw a resonance structure here, the electron pull should be reflected in making this carbon more electropositive. And so now, although this is not a strong effect here through the methyl group, but if these two atoms here will connect, bring in the two methyl groups here then on the same side. This would explain the preference for this regioisomer. And make sure if you look at this in the handouts, and that's why I reversed this here. In the handouts, I have written the both regioisomers in the opposite way. In the handout, this one is here and this one is here. And then I just copied the table, and this is how the mistake came. Yeah?
I don't understand it. The methyl group, we have to, there is a positive, a slightly positive charge.
On this methyl group?
Yes.
No, I would not say so. I would argue that yeah. Okay, I would argue that if I have, let's just take a proton. If I have this, if I draw a resonance structure, this would be the resonance structure. And so the positive charge should be here. And at the same time, you know that nucleophiles will attack here in a conjugated fashion. They will also not attack here, right? So in any way, also without the protonation or without the loose acid, in an alpha-beta unsaturated ketone, this carbon has a positive charge, which will increase the polarization as we protonate or put a Lewis acid on this. So very good. We have found an argument that boron trifluoride would like to coordinate this carbonyl group rather than this carbonyl group, because this should be more electron rich, and thereby we can understand this regioselectivity. Now, tin tetrachloride is apparently preferring the other regioisomer, and this tells you that it is coordinating apparently with this carbonyl group. Has anyone a good idea why this is? Yeah? Yes, exactly. And again, this is something we saw already in the Aldol reaction, that it is very important how many free coordination sites it's very important how many free coordination sites your Lewis acid has. Boron trifluoride has exactly 1, because the fluoride cannot be exchanged on a boron. The bond is simply too strong, and therefore 1 open coordination site. And then if it has the choice, the more electron-rich carbonyl compound it will prefer. Tin tetrachloride, tin can be hexacoordinated anyhow. However, also chloride is quite easily displaced. So no matter how many chlorines I will draw in here, clearly the tin has 2 vacant coordination sites, and therefore it can form a chelate here, which is more stable than the monocoordination by itself, and therefore this carbonyl group will be activated, which then will result in an increased positive charge on this carbon. All right, very good. So I think there are a couple of more of these type of examples, which I would simply recommend that you look at them and see if you understand them. I have some more of these regio isomeric systems. Now here we just said that we can only control the stereochemistry in a relative way, and since we do not have any type of chiral information here, we cannot control the absolute stereochemistry. However, this is also possible, and there are many, many ways to do this. I just would like to give you one example which you already know. From the aldol type chemistry, if you want to also have control of the absolute stereochemistry in your Diels-Alder product, you need somewhat from somewhere chiral information. And one very common way is that you will functionalize your dienophile, which very often has a carbonyl group, electron withdrawing, so these are good substrates for the dienophile. You will functionalize it with some kind of a chiral group to have chiral information in there. And there are many. The one you know from the Diels-Alder reaction already is also working in the Diels-Alder reaction, and these are again the oxazolidinones, the Evans auxiliary and again, we talked about this. These can be derived from amino acids. This is derived with the isopropyl group from the amino acid valine. So that is why it's very often abbreviated, this whole group here, just as XV. So very often you find this written as this. with a V is denoting that you have the auxiliary which is derived from the amino acid valent. And I think you can immediately see that if we have a Lewis acid now, which is able to chelate both of these carbonyl groups, this will fix this conformation here. And if this conformation is now the one which will react with the diene, if the backside of the double bond is blocked, any type of diene can only approach from the front. And the one thing you have to consider here, nevertheless, is you could have rotation around this bond. The pi system will certainly stay in the plane. However, this conformation would also be a logical one. However, we talked about this. We have an allylic system here. And from this allylic system, these groups do not want to be in the same plane because of the 1,3 allylic strain. And so therefore you can see that if you choose a substrate like this, the conformation is, or there is basically this conformation available. The backside of the double bond is shielded by the substituent you bring in here, the chiral information you have here. And so therefore, if this now gets treated, the cyclopentadiene as a diene here, and the Lewis acid, in this case, which was used, is diethyl aluminum chloride. Again, with the same idea. The alkyl groups will not be exchanging, but the chlorine atom can. The chlorine atom can, so you have two open coordination sites for coordinating the two open sites here to form such a chelate here. Now, interestingly enough, you might wonder, we just said boron trifluoride is not exchanging a fluoride. The aluminum chlorides do it, but sometimes they also do it quite reluctantly. And so here in this case, a chloride has to go. And the question is, where does it go? And interestingly enough, what you do here, you use more than one equivalent. You use two equivalents. And in the handouts, I have given you more of the details on how the selectivity is changing with the equivalence of aluminum dichloride you use. But by using a second equivalent diethyl aluminum chloride, you basically add an acceptor for that chloride atom, which has to leave here in order that this chelation can occur. So again, quite often important is, in such cases, also stoichiometry and to be aware of effects like this. So, but nevertheless, you can very nicely form the chelate. you have very good endo control. So you will form exclusively the endo product where this substituent is on the side of the pi phase. However, there are two different endo products. These are diastereomeric to each other because we have the chiral auxiliary here, which of course has a constant, stereocenter here. So these two are now formed in a ratio of 94:6, and this is a diastereomeric ratio. But if you cleave the auxiliary, and we said that peroxides are particularly good for this, then you would form here, after cleaving the auxiliary, you have been forming now two enantiomers. And if in the process of cleaving nothing will happen with your stereocenter here, then you would expect that the ratios are still the same. So you would have an enantiomeric ratio now of 94:6. And this is very often not given as an enantiomeric ratio, but people like to give enantiomeric excess, which is abbreviated as EE. And this is now the difference between these two numbers, which has to give 100 in the end, but 94 minus 6 is 88. So you also find very often that one says that now these two enantiomers has formed with an enantiomeric excess of 88%, and you find 88% EE. From Arkansas, Professor Gawley, there's a very famous article in Journal of Organic Chemistry. I should also post this in our handouts, where he said that you should not use EE. He has made a big splash in explaining why this is not a good way. It's a very interesting article. You should read it. On the other hand, this is very, very common. And I believe at least for the next 50 years, we will probably still keep using this. OK, so here you had one example. I have given you some more, but you have basically one example which should show you how it is possible to also control absolute stereochemistry by bringing chiral information in a type of an auxiliary into the substrate. And without that, I want to show you an example with this. But there's, of course, also the way to bring the chiral information into your Lewis acid. You could have chiral ligands here, so then you would have a chiral catalyst and not have stoichiometric information of your auxiliary in your substrate. And that is another strategy, even more difficult to realize, but of course it gives you the way to arrive at enantiomeric enriched products without first helping chiral information to the substrate in the meantime. So there's also in the handouts is one example, but I would like to make sure I have just given it to show to you, but this is clearly not part of this lecture here. All right. We will go back to one more Diels-Alder reaction a little bit later, probably next hour, because I want to cover some different reaction first on this. We will move now to some 1,3 dipolar cycloadditions. Which I would like to show you. Now, the 1,3 dipolar cycloadditions are also very widely used, and they are especially used a lot in pharmaceutical industry to make heteroaromatics. And since just about any drug we have on the market contains nitrogen and oxygen cycles, and especially aromatic cycles, these have great importance for such applications. The idea of a 1,3 dipolar cycloaddition is that you can have in the most simplest way a system like this which contains heteroatoms, and you can draw different resonance structures which will make clear that this is indeed a 1,3 dipolar, and you will see this in just a moment when we go to concrete examples. And these type of systems also undergo cycloadditions very nicely. Let me put in just generic some charges here. You will see very often we have a nitrogen here, which then bears a formal positive charge. And you form such heterocycles. And these reactions are also very often carried out with alkynes. If we have. Which then very often, if we have free electron pairs here on our X substituent, will lead to an aromatic system, to an heteroaromatic system, which is very stable, of course. And so these type of reactions are thermodynamically greatly favored. It's called a 1,3 dipolar addition because we have 1,3 dipoles available or present. And let me just highlight a few. I think there are a number you know already. Diazomethane, for example. Which I can draw like this, or if I want to show the one-street dipolar character, for example, I can draw it like this. However, this is the much more common way to denote this. So diazomethane azides fall into the category of one-street dipoles. Or let me put down one, of course, you also know very well. And this is ozone. I have given you in the handouts as many as 18 different of these one-street dipoles. You can just about any type of heteroatom combination with oxygens and nitrogens have been realized. So you can look at them at the handouts. I will highlight a few in the reactions in just a moment. Basically, as I say, any type of combination has been realized very successfully. Now, cycloadditions with these are called one-street dipolar cycloadditions. But in the terminology to classify the cycloadditions, this is called a three plus two cycloaddition, because you always count simply the atoms which are involved in that cycloaddition, and make sure you don't mix it up. You're not counting the electrons. So again, I'm moving 4 plus 2 pi electrons here. Nevertheless, it's a 3 plus 2 cycloaddition, because in that terminology, you count the atoms. With the Diels-Alder reaction, since it's 4 plus 2 electrons and 4 plus 2 atoms, one could think of it either way. So let's briefly understand that these are thermally allowed reactions. So let's look at the orbitals. For our, in this case, you would call it a dipolarophile. Like a dienophile, but since it's now reacting with the 1,3 dipole, people call it sometimes a dipolarophile, and this is of course your 1,3 dipole. The HOMO-LUMO analysis for our alkene here is simple. It's in the same way as we did it before. We have 2 pi electrons which reside in the pi orbital, which has no node here. And then we have an empty pi star orbital, which has 1 node. And so again, this is the LUMO here. And this is the HOMO. With our 1,3 dipole, we have 3 atoms to consider. The lowest orbital will have no node here. It's occupied. Next orbital will have 1 node, and if you draw the wave functions in a very crude way here on top of this, then you see that this 1 node must go through the center, which makes this orbital 0 here. And so the graphical representation then looks like this, that in the center you just make a dot to show that the orbital function of this lobe here is 0. Also, this orbital is filled. As you can see, we have to fill in 4 pi electrons. And then we have a third orbital, which now has to have 2 nodes. So I color them this way. With the nodes here on this position. And this is unoccupied. So the HOMO is here, and the LUMO energy is here. And now you can immediately see, if I combine the HOMO with the LUMO here, that these orbital overlap is matching, because I have at the end orbital nodes which have the same color, the same way as I have it here. If I do the other combination, if I do the LUMO interaction with the HOMO here, I have different orbital nodes on the ends here. I have different orbital nodes at the end. So again, this is also matching. So therefore, this is a thermally allowed process. With the Diels-Alder reaction, we have said that there is a Diels-Alder reaction with normal electron demand and with inverse electron demand. Interestingly enough, the HOMO-LUMO energies of the dipoles somehow are between the HOMO-LUMO energies of the dipolarophiles. So you find very often with the same dipolarophile reactions with an electron-rich alkene, which then would go through HOMO of the alkene and the LUMO of the dipolarophile, and you find it without that you're changing anything on the dipolarophile. You also find it with electron-poor alkenes the other way around. The rule of thumb is that basically dipoles will react both well with electron-rich and also electron-poor dipolarophiles. The one name you should associate with 1,3 dipolar cycloadditions is Professor Rolf Hüsken. He's a professor at the Ludwig-Maximilian University of Munich. He developed this in the 60s and in the 70s. He's now above 80. He's still every day in his office at the LMU Munich, and he's never missing a seminar. So this shows you clearly that chemistry helps you to stay young. And whenever you give a seminar there, he is always asking the sharpest question. And so you have to really make sure that you're not making mistakes if you give talks in front of him. And he developed this all edifice and all these reactions I've shown you now in the 60s and the 70s. He was actually nominated for the Nobel Prize once for his work, and unfortunately did not receive it. Okay, let's look at a few reactions. Just for reminding, without that we will go very much into this, but you know that ozonolysis is a very facile reaction. It forms in a 3+2 cycloaddition in an initial one, such an ozonide. And then you know that this breaks, and ultimately, by adding a reducing agent, you cleave the double bonds and form the corresponding aldehydes or ketones. This is a reaction you should know. If not, please review it. We covered this in the third semester quite extensively. Let's look at a reaction you might not really known so far, but which is extremely useful. And these are reactions which are involving nitrones. What is a nitrone? A nitrone is a compound which looks like this. And you can probably get an idea how you would synthesize this. If you start from an aldehyde and treat this aldehyde with N-methyl hydroxylamine, then by the chemistry, of course, you're used to normal addition of the nucleophilic nitrogen to the carbonyl compound, and then elimination of water. And I asked you to work out the complete mechanism for yourself. You will create actually what I have already written on the board, this type of nitrone. And these nitrones readily react with alkenes in this fashion. To generate this type of heterocycle, which is called an isoxazolene. Now you might wonder, what is that anything good for? The typical reaction you follow on such a such a nitrone cycloaddition is a hydrogenolysis. You will hydrogenate the nitrogen-oxygen bond, and what this allows you to synthesize is that you have added onto your alkene another carbon fragment which comes from your aldehyde, and moreover you have added a nitrogen and oxygen functionality. What I did not do good here is, and nobody had complained, is that I have, oh no, it's okay, everything is fine. So you might wonder if this is for anything really useful. Let me point out one thing and then allow me to use the last 2 minutes for an actual application. One of the problems here in these type of reactions is if you have unsymmetrical alkenes. Because again, what we discussed for the Diels-Alder reaction is also then true for these type of reactions, that you can form regioisomers. If you only have simple alkyl substituents here, you will not be able to control this very well. So the nitrone reactions have a special meaning if you do it in an intramolecular way, because this way, because you have tethered your substrates together, problems of regioselectivity will not occur. And let me show you, and I'm sure you will be convinced after I've shown you that example, that if you learned nothing else in this lecture today, that it was worthwhile to wait for the end. So let's look at one intramolecular application. Have this nitrone here, which has this side arm with these acrylic ester here. And so your 1,3 dipolar reaction takes place between these 5 atoms here in an intramolecular way. And I would ask you then also to see at home for yourself that the product I'm writing now is the correct one. So you can create this compound out of this. And if you do now a hydrogenolysis, you cleave the nitrogen oxygen bond here. And then if you make the benzyl ester out of the alcohol, you are obtaining this molecule. Does anyone know what we have synthesized? I can see that your criminal activity is not very high, which is of course very good. The compound has been made a big splash this weekend in the news because there were all these news informations that you can find it in Red Bull Cola. We have synthesized cocaine here. You see, it's not particularly hard to make it. Okay, with this, I wish you nice weekend, long weekend. Tuesday, as you know, there's no lecture. And with this, I hope you will look at some of the handouts we have and then have a good holiday. Thank you.